Good evening, ladies and gentlemen, and welcome to 16 Nearly Impossible Issues for Evolutionists to Answer. There's my email address in case you should care to use it. The main objective is to sketch the 16 issues, which are mostly scientific, and then to show how the evolutionist responses, if they exist, fall short or violate basic, well-known laws of mathematics, physics, and chemistry. You might recognize some of these lines from Here We Go from 1949. They illustrate what it was like when Columbus was trying to battle Ferdinand and Isabella to show that the world is round. And you might also recognize these from John Godfrey Sachs, The Blind Man and the Elephant. Each was partly in the right and all were in the wrong. We each come with our own perspectives. This quote you might recall from Miracle on 34th Street, where the Santa Claus character said, "You've heard of the French nation, the British nation. Well, this is the imagination." And that's oftentimes what the solutions will begin to resemble. And also the Santa Claus character said, "I have great respect for," well, I substituted the word science, and great contempt for meddling amateurs who go about practicing it. One last one. Thomas Edison, who probably had more patents in his day than anybody else, said, "We don't know a millionth of 1% about anything." Here are then some preliminaries. 4 philosophical schools of thought. Absolutist, which means somebody told you. Empirical, which means somebody tested it. Pragmatic, which means somebody found that something works. And existential, which means that somebody showed that something occurred. Now, of these, I'm going to choose the empirical school of thought because it's the most appropriate. Sometimes we'll end up instead with the impossible becomes the possible the plausible, the plausible the probable, and the probable the certain. This is not science. Show me why the impossible should become the possible, and so forth, before going on any further. Otherwise, we're saying we believe in miracles over science. There are also some non-empirical categories like the historical, the spiritual, and the unsensed. They don't belong in a talk like this. They might belong in the courtroom, however, circumstantial evidence being what it is. And verified scientific laws don't displace other verified scientific laws. Or, as one person has put it, the new science better agree with the old science. That was said to Stephen Wolfram on 1 February 2003 at Caltech with his alma mater and 3 skeptical professors, and I was there to see this talk. Let me contrast also interpolation versus extrapolation. Interpolation is when we're trying to fill in points between known points, whereas extrapolation is we're trying to extend beyond the boundaries of known points. And extrapolation is fraught with mischief, much more so than interpolation is. Also, the 3 laws of thermodynamics. The first one is you can't win. The best you can do is break even. The second one is you can only break even at absolute zero. And the third one is you can't reach absolute zero. There's also a 0th law that says you must play the game. And so the conclusion we'd reach, if we had no other information, is you must lose. Now, also people tend to think that evolution can only describe things that are biological nature. Somebody supplied me with the covers of 9 evolution textbooks which had nothing to do with biological evolution, but rather with cosmological. Here are those 9 covers if you should care to look at them later. So evolution just simply means changing. It can refer to a whole other set of things besides just biological. Now for the 16 issues themselves. Okay, now that you're all speed readers, we can go home because you've immediately comprehended all 16, correct? No? Okay. Well, in that case, I'll spell them out. In cosmology, issue number 1, why does anything exist? Issue number 2, did the universe always exist? Issue number 3, did the universe cause itself to exist? Issue number 4, how can the universe avoid heat death? Issue number 5, how can any material travel faster than the speed of light? In the physics and chemistry section, issue number 6, what is the origin, transportation, and distribution of carbon? Issue number 7, how do any stars exist? Issue number 8, how do moons form? Issue number 9, What is the ongoing source of comets? Issue number 10. How do any elements heavier than iron exist? In the biochemistry, biology, and information section, issue number 11. How do peptide bonds exist? Issue number 12. How do proteins have only L or left-handed amino acids? Issue number 13. What turned non-life into life? Issue number 14. How does metamorphosis occur? Issue number 15. How do major morphological changes occur? Issue number 16. What creates information from gibberish? We start off then with issue number 1. Why does anything exist? Well, if nothing exists, we have no space, no material, no people, no meaning. We have nothing, and from nothing, nothing comes. Might as well start off with Roget's pocket thesaurus. Want to take a guess among the 1,000 categories of synonyms and antonyms which we can study the language from? Want to take a guess what issue number 1 is? Existence. It stands to reason that if issue number 1 is existence, then the latter categories might have something to do with the possible causes of existence. So we have a number of questions to ask. One is, why this particular total mass? It's been said that we have 10 to the 80th atoms in the universe. Why not 10 to the 79th? Why not 10 to the 81st? And why this particular distribution of mass? It's hardly uniform across the universe. It's in clumps all over the place. That particular notion will come up again and again. And why is the amount of matter much greater, if you like, than the amount of antimatter? Now, to these questions, the evolutionist generally has no particular answer. In fact, it goes against the grain of much of what they have to say. I need to also say something about quantum fluctuations. That's the notion these days that nothing can turn into everything. Really? What happens when a particle and an antiparticle, which they believe can come out of nothing, come together? Do they form nothing again? No. Instead, they form energy while annihilating each other. If we were to repeat that process over and over and over again, we would be able to form unlimited amounts of energy from nothing. What law of thermodynamics does that violate? Anybody? Yes. The first law indeed. Issue number 2. Did the universe always exist? No. Otherwise, we wouldn't be here. Everything would have already dissipated. Now, to that we have a choice. Is the universe open or closed? If it's open, then that can allow the possibility of outside entities in, like, say, a god or a creator. If, however, the universe is closed, then the thermodynamics determine the fate of the universe. Like we'd said earlier about you must lose. Issue number 3, did the universe cause itself to exist? Well, I've had people answer that previous question in the affirmative. And then when we come to this question, they also answered in the affirmative, not realizing that the two disagree with each other. No. Else the universe would have had to have existed before it existed to cause itself to exist. Or the universe would have had to have existed and not existed at the same time in the same context. Either one of them is a logical contradiction. We can then use these 3 issues to form a cosmological argument. Cosmological argument is to show that the cause of the universe must be outside the universe. So from issue number 1, does the universe exist? We say yes. If no, well, then there are some hospitals down the road. You can put some white coats on and get trapped inside if you like. Issue number 2, did the universe always exist? The answer is no. Did the universe cause itself to exist? From issue number 3, and the answer is no again. Therefore, the universe has no material cause because everything else would be a subset thereof. It only leaves us with 2 possibilities. Either the universe has no cause, in which case you're an Eastern mystic, the conversation ends because it's not even scientific anymore. Or the universe has a cause, but it must be immaterial. Now choose from the following list of possible immaterial causes. Fairies, leprechauns, gnomes, my favorite flying spaghetti monster, God, you add to the list, and some people are adding to the list, quantum fluctuations. Oh, by the way, only God even has any testimony. So if somebody tells me that my theory is no better than that of a flying spaghetti monster, I'll turn to that individual kindly, hopefully, and say, I don't believe flying spaghetti monster. You do. And I never get an argument at that point. It's not the creationists who believe in the flying spaghetti monster. It's the evolutionists. At least that's what I claim. We could also rearrange these into a waterfall chart of sorts. Issue number one, does the universe exist? No. Well, that would be obviously false, so we say yes. And then we say the universe has a cause? Yes, because otherwise it would be unscientific. And then we say, is the cause material or immaterial? Well, let's assume it's material and see what happens. Issue two, does the universe always exist? No, because otherwise it violates the second law. Issue number three, is the universe self-cause? No, otherwise it violates logic, and we're back to the immaterial choices that we had earlier. It's powerful stuff because people recognize it forms a mutually disjoint decomposition of the set of choices, meaning there are no other choices, and there never will be any other choices. These are the only ones that will ever be the case. Issue number four, how can the universe avoid heat death? By the way, contrary to the picture, I'm not referring to the universe heating up indefinitely, but rather losing its heat. And the answer is, we can't. The universe can't avoid heat death if thermodynamics are the guide of it. The universe will completely dissipate, and forever after that point, there will be no motivation of anything to do anything. Instead, it will be, as the mobsters put it, room temperature. The room temperature of the universe is about 2.7 degrees Kelvin. Is there any hope for anything behaving otherwise? Well, the new science better agree with the old science, and the thermodynamics are still there. Whether you want to use Roger Penrose's book, Cycles of Time, or otherwise. Issue number five. How can any material travel faster than the speed of light? Oh, you didn't think any could? Well, those who would involve themselves in the Big Bang, despite the fact there's no observational evidence of anything traveling faster than the speed of light, must posit such a thing in order to have everything more or less anisotropic, that is, at 2.7 degrees Kelvin. How would anybody know that such a thing ever took place? Is there any observational evidence? Not that I know of. And why not at some other time? And why only at one time? And also, there's the matter of the graceful exit problem. That is, how do you get it from, as I call it, hyperinflating back down to its normal inflation? Somebody in 1982 claimed to have solved a problem like that. I think it's more a proposal. Hugh Ross's reasons to believe has no answers to questions like this. That is, their organization. I didn't get to talk to Hugh himself. Nor do they have any answers to the next issue. Issue number six. What is the origin, transportation, and distribution of carbon? Now, I'd like some help from the audience. This picture depicts what examples of carbon that are either visible or invisible. One example at a time, please. Anybody at all? Yes?
Diamonds.
Diamond, of course, is one. What's another one?
Coal.
Coal. Another. Yes?
Carbon-14.
Well, carbon-14 is part of the carbon of any living organism. I'm speaking about what examples of carbon. Anybody else who has not spoken yet? Yes?
The grass.
Yes, the vegetation. Sometimes I call it chia pet material. Okay. Anything else?
Carbon dioxide.
Carbon dioxide. Very good. What else?
The soil.
You always come up with the comic relief. Any other examples?
Oil.
Oil. Well, there might be some. I don't know. It's hard to see. Anything else?
The body.
Body.
Beings.
Huh?
Living beings.
Living beings. Yeah. Well, if they're invisible, I suppose. How about, yes?
If there's a little tiny drop of water in the carbon too. Oh wait, no, sorry.
Nope. Dihydrogen monoxide. No carbon in that. All right. How about carbon monoxide? How about methane? There are all sorts of chemicals that have carbon in them. You see that carbon is listed there in our periodic table. My question isn't whether or not there's carbon. My question is, how did it get here in the first place? Now, that was the subject of work done in the late 1940s, early 1950s that resulted in a Nobel Prize in 1983. That's something to do with the triple alpha process, which I'll describe in a moment. Then, as far as the transportation is concerned, the posit is that there are supernovae. That I have a lot to say about tonight. And then the distribution, the mechanism is frankly unknown. In other words, once it arrives on the Earth. Let's start with the triple alpha process. It has, as its origin, only one nuclear resonance, and it could exist only in red giant stars, and that much is already extremely improbable. But then it can be disseminated only by a supernova. And I've got silly questions like, is the transportation just to the Earth? Here's the triple alpha process itself. Two helium atoms, which themselves came from hydrogen in the stars, we'll get to stars in a moment, combine to form a transitory species of beryllium, which is atomic weight 8. And before it can disappear in 10 to the minus 15 seconds, a third one comes to join the fray to form our carbon-12. That's the mechanism. It's extremely improbable. Only in the later stages of a red giant can it be even conceived of. Now, I have something to say about the matter of the supernovae. There'll be a lot of math in this, so hold on tight. Let's suppose that we even have a supernova. Now, you can see that white area is the so-called clear-out area for about 0 to 30 light years away from the middle of supernova, and from 30 light years out to the end is about where all the material is going to be. At least that's what I'm positing. And I have various symbols up there to describe, the carbon being M2 or prime or double prime. The shell volume is in the lower part there is V2. That's the area from 30 to 100 light years. The Earth's volume is just V1. The frustum volume would be all the way out to the end, starting with the Earth. I call it V1 prime, and Earth's carbon itself is M1. I'll pick that up later. I'm just going to give some basic assumptions regarding the values of these kinds of things. We can talk about that later. And suppose we have a 13.7 billion year universe, and the remnants from the supernova scatter linearly and radially in all directions. That's the assumption I'm going to make, rather than that they come back around. That's for another thing. The supernova shell volume I calculated right there. The inner radius is 30 light years. The outer radius is 100 light years, as we said earlier. These are also some other basic assumptions. We have 6 supernovae that form one sun, and the mass of the sun-sized stars, if it's all carbon, is that value, and a giant-sized star, well, you have to multiply it by a factor, n. And then we have some more things going on if we just have a regular star instead of an all-carbon star. In other words, you have to reduce it by a certain amount. The gravity factor, by the way, is 0.1. That's our figure that we saw earlier. It's the same one. Now, calculate some of this stuff. Let's suppose that we have 3 supernovas per 100 years. That's about what it's assumed to be at most. Well, then, within 33 light years of the Earth, we'll have 86, and if we have 100, multiply it by 100 divided by 33 cubed, and you get up with 2,383 supernovas. That's all you have to work with. If, on the other hand, you only have 2 supernovas per 100 years, then it reduces down to 57 within 33 light years, or 1,589 within 100. Now, if we have just the Earth volume, that's what the ratio is going to be. And if it's relative to the Earth frustum, it's going to be that. In other words, there's going to be just way too many supernovas to account for. There would be no hope of that. So instead, we're going to take it as these instead, where we've done the complete calculation, and instead it's going to be 66,408 or 221,360,000. That's the number you'll actually need. Now, if, in fact, those assumptions hold, then you can see that if we have 3 supernovas per 100 years, we're off by a factor of 26. That means you'd have to have 26 times more supernovas as could possibly exist to account for Earth's carbon. That's if you have an all-carbon star. That's where everything is carbon, and it blasts everything out in all directions, leaving nothing behind. In a more normal circumstance, the figure will instead be 92,890. If instead you have only 2 supernovas per 100 years, then you'll be off by a factor of 40 in an all-carbon star, or 139,306 for a regular star. Those results I've summarized in this table. There you see it. Conclusion: the Milky Way galaxy supernovas cannot possibly account for Earth's carbon. Now, there are certain things that I have not brought into the picture, like carbon swinging back around like that, or being swept up by gravity from other places, including the Earth. And somebody's actually thought that the calculation might be way off. I'm just going to use this as a naive notion of a calculation so that in case anybody wants to come along and critique it, they can do so later. But that would be how the public would generally view these kinds of things, rather than the more complicated scenarios. As far as the distribution is concerned, you can see in this world coal deposits map that most of the coal is in places like Siberia, in eastern Australia, through the Midlands of the United States and into Canada and the rest. Where would we expect to see carbon, though, forming coal? Where the vegetation would be. Like, for example, in the Amazon region, you can see there's hardly anything there, and there's hardly anything in Central Africa where you'd expect a lot of vegetation to see. So this is a good illustration of where the carbon exists in clumps in places you wouldn't expect, and it doesn't exist in places you would. And even for the places where it does, you see it's not, like, for example, in the United States, there's nothing between those two bands either. Not only that, but you have to account for miles deep, thousands of miles long solid coal beds in other places, several places throughout the Earth. I would contend that neither the creationists nor the evolutionists have the right answer to this one either, because it's so deep. You'd also have to account for the fact that there are other deposits, which I'll talk about later, which would be swept away if you had a global flood doing this. Issue number 7, how do any stars exist? Well, let's suppose that we start off with all the mass contained inside an infinitesimal volume. That's a volume that's arbitrarily small, but not zero. And then you have a Big Bang. There are other scenarios possible too. Let's just take this one. Let's recall Newton's first law. Does anybody recall what Newton's first law is? Anybody? Anybody have any physics? Okay. All right. Well, maybe you have and you're not willing to speak. Yes? An object that's in motion tends to stay in motion. An object at rest tends to stay at rest. Now, what will happen to the particles in a Big Bang if Newton's laws apply? They will keep going and going and going and never stop going away from each other. What do we need to have a star? The compression of gases. We have a hard enough time here on the Earth, even with partial compression already here, to compress gases. We have to have a container which is much smaller than the Earth. The temperature goes from hot to cold instead of cold to hot like you'd have to have in outer space. And once you get that solid or liquid material from the gas, what happens if you remove the container? Well, it'll go back to the gas that it was. Now, let's think about whether or not we can have anything out there in outer space. We have 2.7 degrees Kelvin out there, and gases in that particular state, if they are brought together, first of all, they will liberate heat, because that would be what would happen, so they'd actually get colder than they would instead of getting hotter. But even if they were to get hotter, they would then tend to drive each other apart because of the heat. In other words, we shouldn't really have any stars at all, if that's all we had to know. And there's also a flip side. Suppose that we have a generous 20 billion years to work with. Suppose we even had, instead of the ordinary 13.7 billion years. Somebody has estimated that there are at least 10 to the 21st stars in the universe. How they come to this number, I don't know. And I also heard recently about that it should be multiplied by 10, whatever the previous number was. There's 10 times as many galaxies as there thought to be. Let's divide the number of stars in the universe by the number of years. And we should come up with 50 billion stars being produced every year for every one of those 20 billion years. Somehow I don't remember seeing in the newspaper, on radio or television, or on the internet that we had met our quota of 50 billion stars last year. Have you seen anything like that? If you have, let me know, because I haven't. Now, you could be decreasing the number of stars per year or increasing. However, it still has to be an average of 50 billion stars for every one of those years. This is where I have the problems, trying to come up with some of those kinds of answers. Issue number 8, how do moons form? Well, let's start with the moon that the Earth has. I'm going to contend that there's no solid moon you could ever get from it. Let's suppose that we use the impact theory first. What's the most likely thing that's going to occur if an object, maybe the size of a moon, or even Mars, comes and hits the Earth? What's the most likely thing to occur? It's just going to stay in the Earth. It might kick up a little dust, but that's about it. So you'd have to have it going at a rather rapid speed that is, well, the bigger the object, the less likely it's going to have the speed either. But let's suppose that it actually does impact the Earth and blow up some material. It'll have to exceed the Roche limit. And what is that? Well, it's about 1 to 2% above the Earth, and above that point, you might get some sort of coalescence. But if you never reach that point, then tidal forces will overwhelm the material because it's only held together by gravity, and it will fall back to the Earth, and there goes your moon experiment. So you'd have to go up at least that high, but you better not be going too fast. If you reach escape velocity, then it will just keep going away from the Earth, and you'll never see it again, more than likely. On the other hand, it can't be going too slow, because otherwise it will still fall back to the Earth, Roche limit or not. Also, even if you get the material into the right area, it will have to co-locate, but not just that, it will also have to compactify with no known source of compactification. The moon is compact, so we know that it has to have done that. Also, you'd have to have the right tangential velocity imparted to the material to cause it to orbit. It also has to be perpendicular. There's no known source of that force. And we who have been in aerospace know the exact conditions for an orbit. By the way, if it were to come straight out, which is the more likely prospect of having this work, and we have a tangential force like that, what is the most likely orbit going to be? It's going to be geosynchronous. In other words, orbiting the Earth once a day. How often does the moon actually orbit the Earth? Anybody? Yes?
About once every 30 days.
Yes, once a month. That's how I got our name Month. So what we're observing does not agree with what the most likely scenario would dictate. Here's an interesting quote from Wikipedia. Since tidal forces overwhelm the gravity that might hold the satellite together within the Roche limit, no satellite can gravitationally coalesce out of smaller particles within that limit. And if the moon were to exist long enough, it's believed that if it were to come back in the direction of the Earth, that it would scatter for that reason once it reached the Roche limit. Recognizing these problems, some recent papers have come out. This one came out 9 years ago, where instead of just an ordinary impact, we had something that looked like that. I would call that a Pinocchio effect. And there was a problem, however, with the Pinocchio effect, and that is that the potassium didn't agree with what should have been expected. So we had a larger Pinocchio effect, like so, where instead you're forming moonlets. The only problem is, of course, none of the basic questions that I've been asking has ever been answered. They still are there. You still have, well, in this case, you'd have to exceed Roche limit. You'd have to have the compactification, besides the coalescing. You'd have to have the right orbit. You can't go too fast. All those objections are still there. They really don't answer a question like this. They're just trying to get it out there far enough and to stay there. Okay, and that was this year. Look at that, 2016. Good luck, guys. Now, in the case of other planets, I have a silly question to ask. How are you going to get a moon to go around a gaseous planet like Jupiter, Saturn, Uranus, or Neptune, and they have most of the moons, by blasting the planet? I don't think so. If anything will go into the planet, it will get absorbed by the atmosphere or the material that the planet is made of at the core. So I would contend you can't get it that way. Now, some people have actually considered the nebular hypothesis, and that is everything was forming at about the same time. In that case, I have another question to ask, and that is, how did the planets get to be gaseous and their moons solid, if it's the same material? We also don't have any binary combinations, and we also don't have any moons around Venus, which is another problem that's never been discussed too well. The capture theory is regarded as being too coincidental, and among other things, it doesn't agree with the isotope ratios that you'd have to have. That is, we see more or less common isotopes instead of differing isotopes, and if it were capture theory, we should expect to see differing isotopes. There's also no evidence of other tries. Now, you might recall a few years ago when we had a meteorite coming in a direction, and all the things that resulted therefrom. Think what would happen if you saw a moon coming in your direction. So there really are no plausible theories out there. Issue number 9. What is the ongoing source of comets? Comets can take place as either short term, which is less than 200 years in orbit, or longer term. Some of them are believed to be explained by the Kuiper belt and the interplanetary disk. However, others, mostly the papers say long term, but I did run into one that claims the short term is actually the problem, require some other explanation, namely the Oort cloud, spelled O-O-R-T. What, might you ask, is an Oort cloud? It's an automatic picture of dirty snowballs or whatever else comets are made of. Conveniently, of course, because otherwise we'll have the comets falling into the sun, losing their mass, or otherwise being lost. When I hear about things like the Oort cloud, that it's very far away and cold, I have images of Santa Claus. And maybe that's what the theory is like too. There's no actual evidence that's yet ever been produced for an Oort cloud, and there are no other theories that are available. Issue number 10. How do any elements heavier than iron exist? In the periodic table, you notice that iron is located in the 4th row between manganese on the left and cobalt on the right. This graph is known as the average binding energy per nucleon graph, which is in Chapter 9, Section 6 of this modern physics book. You'll notice that at the left side of the graph, helium is at a maximum, local maximum, and then it goes down, kind of reflecting that carbon problem. And then it goes back up, and what elements does it hit at the maximum of the graph? What's that element up there? It says Fe. Iron, that's right. And then it trails off to uranium. If you're going to start off with low number of mass and try to build up to get the whole periodic table, you're going to run into a problem. How do you get past iron? Iron is more favored to form than any other element is favored to form. According to this graph, you'd have to start off with already existing uranium and go backwards. But how are you going to get the already existing uranium? What is the proposed solution here? Our old friend, a supernova. That is, through the process, there's like RNS, I think is what they're called. Through these processes, it's believed that you can get the higher and higher element numbers. I've got a different problem. Won't that supernova blast everything out into smithereens in all directions anyway? How will you have any ores on the Earth, or anywhere else for that matter? See, this is kind of the problem that we run into. There's no explanation for the transportation and distribution problems in this case either. Here is a chart of the world's mineral deposits. Most of the precious materials are actually located in South Africa, Russia, or sometimes China. In other words, the political hotspots. But they're not scattered all over the Earth. Otherwise, they would not be economically mineable or viable. In the biochemistry, biology, and information section, issue number 11, how do peptide bonds exist? Here is a model of an amino acid. On this side is a nitrogen atom connected to 2 hydrogen atoms. Forms an amine group. You think of ammonia, it would have a 3rd hydrogen. In the middle, a hydrogen atom and a functional group, which can either be a hydrogen or any of other 19 other choices. On the other side, we have a carbon, doubly bonded to an oxygen, and also singly bonded to an oxygen, which is bonded to a hydrogen. COOH, carboxylic acid. Base, acid. They should connect together and form a bond. In fact, if they do get together, they'll form a peptide bond, as you can see. What molecule is lost when the peptide bond is formed?
Water.
Water. That's correct. Now, have you ever heard that little thing from Darwin that says that life began in a warm little pond? Just how is that going to occur? When a water molecule must drop out, not be absorbed by the amino acids. This is a problem. In fact, in bodies, we have to depend upon things that are called rough endoplasmic reticulum ribosomes in order to get them to form together. Otherwise, you won't. So, if you can't get it in a warm little pond, where there aren't any such ribosomes yet, I don't know how they're going to find each other in dry land. But let's suppose they do. You have a choice of an atmosphere over the dry land, either oxidizing or reducing. If it's an oxidizing atmosphere, let's just take oxygen as being the agent, then the oxygen will break the bonds and maybe destroy the amino acids in the process. On the other hand, if it's a reducing atmosphere, then there won't be any ozone. And the UV rays come in and they will destroy the bonds and maybe the amino acids. In other words, there's no good naturalistic scenarios by which you can get peptide bonds without already existing bodies. This is the form of an amino acid we saw earlier, and that's the pattern. Proteins chain by forming peptide bonds. If you don't have any bonds, you don't have any proteins, you don't have any enzymes, you don't have any life. And, as we all know, without biochemistry, it's amino world. Issue number 12. How do proteins have only left-handed amino acids? Now, in my hands are mirror images of the amino acids. Can you see that these are mirror images? Okay? You can also look at the figure on the screen. However, it's not possible to stick one on top of the other so that they match. So the best you can hope for is 2 out of 4. These two will disagree. In other words, the two molecules are different from each other. Sometimes they're called stereoisomers and enantiomers, chiral compounds, non-superimposable mirror images. One of them labeled as left-handed, levorotatory, and the other is dextrorotatory. They can exist as in many inorganic compounds besides the ones I've named here, and other kinds that can have 4 differing entities. But that was the primary one here. The evolutionist comes to the table and he says, I have to start off with a neutral scenario. Neutral ingredients, neutral energy sources, neutral environment. And of course, the amino acids themselves, just left and right-handed, they'll have the same melting point, boiling point, refractive index, vapor pressure, chemical reactivity, density. The only way you can tell them apart is by the fact that one of them rotates plane polarized light in one direction by so many degrees, and the other will rotate it by the same number of degrees in the other direction. It's the only way you can tell them apart. By the way, it's an interesting book, Flaws in the Theory of Evolution by Evan Shute, written by the prodigy Evan Shute. He has something to say about that, just passes it off as more or less within 5 words in his book. Every amino acid in every protein of every species is only left-handed. There are no right-handed ones. Isaac Asimov had no actual retort. He just said, well, it happened that way. If he were here, I'd have asked him, over the entire face of the globe? And no, they don't replicate. In fact, we saw some of the reasons why they wouldn't. You need those ribosomes first before you can even get the hook together. Now, there are dextrorotatory right-handed amino acids in other structures like bacterial cell walls. Otherwise, enzymes, which are proteins, will come and destroy the bacteria. You wouldn't live either because you need bacteria in your intestines. If any bacteria do encounter amino acids, they'll turn any right-handed ones into left-handed ones before trying to digest them. I'd like to read a sentence out of my Morrison and Boyd book that hammers home the point. Page 236. Actually, a paragraph or so. Indeed, we deal with optically active substances to an extent that we may not realize. We eat optically active bread and optically active meat, live in houses, wear clothes, and read books made of optically active cellulose. The proteins that make up our muscles and other tissues, the glycogen in our liver and in our blood, the enzymes and hormones that enable us to grow and that regulate our bodily processes, all these are optically active. Naturally occurring compounds are optically active because the enzymes that bring about their formation and often the raw materials from which they are made are themselves optically active. As to the origin of the optically active enzymes, we can only speculate. The situation is no better now than when this book was being printed in 1972, and the problem was known for more than 100 years before that. Now, left and right-handed amino acids don't form together too well, as illustrated in Evolution, Possible or Impossible by James F. Coppedge. By the way, David Coppedge is the son of this now late professor from Cal State Northridge. But why couldn't you have an all right-handed chain then? It could form as equally well, if you could ever get the chain to form in the first place, as a left-handed chain. For those who might be more inclined academically, here I have tetrahedra together in one cube. For example, the red ones on the outside, that'll form a tetrahedron, and the bond angle between any two of the red ones and the one in the middle is said to be the tetrahedral bond angle. Using ordinary Euclidean geometry, we can calculate that to be exactly the arc cosine of minus 1/3, or 109 degrees, 28 minutes, 16 seconds to the nearest second. This is an exercise that could be done in high school, and I wish the high schools would, in fact, show people how to do so. We didn't learn about it until we were freshmen in college. That'll be the bond angle if every one of those is equal to each other, like methane, carbon tetrachloride, carbon tetrafluoride. If they're different from each other, then we'll have some clue, maybe. Especially, we could apply that notion to help identifying our R groups. That would be the group in the amino acid, because they'll differ from each other depending upon how they're stretching or compressing. Issue number 13. What turned non-life into life? Suppose there's a dead dog. It's been dead long enough, 3-4 days. One small task, Hercules. Breathe life into the dog. I've given you all that it has. The heart, the liver, the lungs, the spleen, the central nervous system, the alimentary canal, the stomach. I've given it all to you. Just breathe life into it. What's the matter? Is this not a small task? Are you not Hercules? Well, maybe the problem is much bigger after all. And if we cannot breathe life into a dead dog, what makes us think that we can breathe life into materials made into a dead dog? Or choose any other creature if you like smaller ones instead? We don't even have that much to work with if all we have is hydrogen. Or maybe that infinitesimal associated with the Big Bang. There is no spontaneous generation. There is no Goldschmidt hopeful monster. And no, there's not this RNA, the hero scenario. That's just a hypothesis. Life only comes from life. That's all we've ever known from Pasteur onward. Issue number 14. How does metamorphosis occur? Here we have a typical metamorphosis of an insect. I'm bypassing the amphibian metamorphosis. You see an egg can hatch into a larva into a pupa into an adult, and the adult will lay the egg. Okay, I'll even give you stages 1, 2, and 4. But would somebody please explain to me how that mushy stuff inside the chrysalis, or the cocoon, turns into an adult? I mean by that the origin of such a process that could have led to such a thing. The young Earth creationists, the old Earth creationists, and the evolutionists have all within the last 5 or 10 years conceded this as a mystery in print.
We might want to look at metamorphosis. Most insects, about 87%, undergo a complete metamorphosis. That is, a larva, such as a caterpillar, builds a cocoon or chrysalis around itself. Its body inside then disintegrates into a thick pulp-like liquid. Days, weeks, or months later, the adult insect emerges one that is dramatically different, amazingly capable, and often beautiful, such as a butterfly. The food, habitat, and behavior of the larva are so different from those of the adult, it's hard to imagine. What mutations could improve a larva? Certainly none that destroyed its nerves, muscles, eyes, brain, and most other organs, as occurs within the cocoon. So even if the larva improved, it later ends up as mush. From the evolutionary standpoint, liquefying complex organs is a giant step in the wrong direction. Millions of changes inside the thick liquid never produce something survivable or advantageous in the outside world until the adult completely forms. How did the genetic material for both larva and adult develop? Which came first, the larva or the adult? What mutations could transform a crawling larva into a flying monarch butterfly that can accurately navigate 3,000 miles using a brain the size of a head of a pin? Indeed, why should a larva evolve in the first place? Because it can't reproduce.
Issue number 15. How do major morphological changes occur? Well, morph means change, so it's kind of like the Rio Grande River or the personal identification number. It's repeating the same word. Here are some typical changes that would have to occur. If you go from fish to amphibian, you go from no metamorphosis to metamorphosis, and you have to change the number of chambers in the heart from 2 to 3. If you go from amphibian to reptile, then you'd have to lose the metamorphosis you gain. You'd also have to change the fertilization from external to internal. If you go from reptile to bird, then you'd have to change from cold-blooded to warm-blooded. I'd really like to see that one. And you'd have to go from scales to feathers. If instead you're going to a mammal, then you go from scales to hair. And if you want to pursue an alternative that nobody does, and that is to go from bird to mammal, then you'd have to go from wings to hands, paws, and hooves, and feathers to hair, whatever. Not one of these changes has any hope of being solved anytime soon. Nobody knows how to do any of them. And these are only 2 examples of them. You might as well also talk about chromosomes. How do you get from one set of chromosomes to another? Even humans. Humans have 46 chromosomes. The nearest one to us is 48. And getting from 48 to 46, I understand, involves a deleterious fusing. Now, one might be able to argue, well, we could go from fishes, or amphibian. My question is, what happens at the transition point to going from one to the other? There's where the spot is that I want to concentrate my arguments, because those are where the weak spots are, especially if nobody has any answers to them. You'd also have to have them true of male and female, co-located to form a colony.
Well, never mind. Evolutionists still insist that feathers evolved from reptile scales, specifically dinosaur scales. And to prove the point, they say that feathers and scales are so similar you can hardly tell them apart. Have you noticed that? One of the first people to say this was Gerhard Heilmann back in 1927. In his book, The Origin of Birds, he says the most striking peculiarity of birds is their plumage, which apparently has nothing at all in common with the scaly covering of reptiles. So much more surprising is it, on examining these structures in the microscope, to learn that the feather is nothing but a further development of the scale. Alfred Romer, very distinguished evolutionist, says birds have been called glorified reptiles. Feathers are in reality almost their only distinctive feature. And he says, although these structures seem quite different from the horny scales that cover a reptile's body, the difference is in reality not very great. Well, you can look in your Encarta encyclopedia, if you have one on your computer, look up feathers, and they will confidently declare that the feather is a horny outgrowth of skin peculiar to the bird, but similar in structure and origin to the scales of fish and reptiles. So I thought we'd do a little test. I had a laboratory technician that worked for me. They had a pet boa constrictor. And I said, hey, the next time that little rascal sheds its skin, why don't you bring it on in and we'll look at it in the microscope, because I understand you can hardly tell a reptile scale from a feather. And so she did. She waited, and when this little rascal shed his skin, and by the way, I want to point out that no snakes were destroyed to do this study. We waited until they shed naturally. She brought the skin in, we put it under the microscope, and we magnified it. And this is what a boa constrictor scale looks like here. You can see the others around it. And as the evolutionists have told us, if you look at them in the microscope at least, they are remarkably similar to a feather. So then I took a picture of a feather, and I want you to see if you can tell the difference. So you may want to clean your glasses or something right now. Have you got this one in mind? Okay. If you get confused, just look at the top. It'll tell you which is which. Okay. That's the scale. This is a feather. What do you think? Should I go back and forth? You got it down? Or, I mean, why do they say they're similar when they're absolutely not similar? In fact, I'll go further than that. They are totally different. Their mature structure is dissimilar, their function is dissimilar, their embryological development is dissimilar, their mechanism of growth is dissimilar, their mechanism of replacement is dissimilar, their chemical composition is dissimilar. And let's just look at the obvious. Scales are like folds in drapery, like drapery pleats. It's all one sheet. That's like when a reptile sheds scales. He doesn't shed them one at a time or two at a time, does he? The whole thing comes off as one sheet. In fact, reptiles typically have two layers, won't they? An outer layer and an underlayer. When they shed the outer layer, then the underlayer is exposed. Why do they do that, by the way? Why do they shed their skin? Because they're growing. Now, I want you to think about this. You get a box through the mail, and you're wondering what's in the box. You open up the box, you know what's in the box? A bigger box. So you shed the outer layer because the underlayer is bigger. You got to think about that a while. Let's look at that boa constrictor skin. The tail's in the direction of the arrows. So to your upper right, that would be the tail. I don't know, 1/4 of a mile up there or something like that at this magnification. And you can see the scales are arranged in rows, sort of on the bias with the long axis of the snake. If we get a hold of the right side and flip it over like the page in a book, this is what the underside of the skin looks like. And so now the tail's in the direction to the upper left corner. And again, for those of you in the cheaper seats, let's magnify this a bit. This is where one scale just fit right underneath here. It fit right in there, so when the skin pulled off, that scale pulled right out of that pocket, like taking your hand out of a glove. And that's the way the scales are put together, is one continuous sheet. Now, feathers are completely different. Feathers grow out of follicles, just like hair. Hair grows out of a hair follicle. Feathers grow out of a feather follicle. But I'm here to tell you there's no such thing as a scale follicle. Now, what is a follicle as it relates to feathers and hair? It's a tube-like depression in the skin. You see it here. Goes down deep in the skin. All of the growth occurs in the bottom in what's called a growth collar. The feather grows out sort of looking like a thick hair. And when it comes out of to the surface of the skin, it all unfolds to make the feather. This is the way the feather follicle looks down in the skin. All of the growth is occurring here, and the feather's alive at this point, but as it makes all of its parts, it dies. It goes through a programmed cell death so that the feather that emerges from the skin is completely dead. This is how it all develops. Inside the shell here, we have what we call a pin feather. If you peel this shell away, you can see that this is the growth region at the bottom. The shaft goes up along the backside there, and then the barbs grow off this growth ring, and those little barbs get longer and longer. They grow from each side and meet at the other side. When the feather comes out of the follicle, the cylinder opens up, the barbs all swing down, and you get this big broad feather out of a hole in the skin that's not much bigger than a shaft. And that's the way each feather grows from living cells, goes through a programmed cell death, and rises up out of the follicle in that way.
Issue number 16. What creates information from gibberish? Suppose I posit the ordinary set of communications that require a sender tuned to a receiver tuned to a sender, and a medium that promotes rather than interferes with communication. We also need an already existing language and context. And we need the two or more parties to perform a sample task as evidence. We have measures for whether or not things like this will work. In Donald Johnson's Programming of Life book, the beginning of chapter 9, it's an interesting statement. The failure of purely physical theories to describe or explain information reflects Shannon's concept of entropy and his measure of news. Information is defined by its independence from physical determination. If it is determined, it is predictable, and thus by definition not information. Yet Darwinian science seemed to be reducing all nature to material causes. In other words, if everything is just physics or just chemistry, then there isn't any information either, because it wouldn't be novel. Also, along for the ride is, if all you start off with random processes, that's all you'll end up with, too. Now, as far as the measures are concerned, we have what is called the autocorrelation function, which those in aerospace might recognize as lining up a sequence against itself and measuring how pseudo-random it is. There's also the glorification known as the ambiguity function, which measures things in range and velocity. And if you want to bury a code, you do work in subjects like this. This is a copy of the second edition of Radar Handbook by Merrill Skolnick. This book is used in virtually every aerospace company in the world. There's a copy of the third edition with Skolnick on the left. I want to compare information entropy and energy entropy. They have the same mathematical forms. So just like we saw entropy earlier, that would be the second law, it also applies to information in precisely the same mathematical way. It's like scrambling words instead of heating gases. All life structures need information. How are you going to get from DNA to the proteins, or the proteins to the DNA, when maybe you've only got one of them at most, but if you even have two of them, they still have to be programmed for each other so that each will recognize the other. Back and forth. This is another one of those chicken and egg problems that we described earlier. Oh, by the way, did I ask the question about the chicken and the egg? Which came first, the chicken or its egg?
Go.
I think somebody said it back in the back. God. But of the two, a hen and a rooster came first. It's not Adam and Steve Rooster. It's not even Guinevere Hen. It's Adam and Eve Chicken. I have pictures of 7 modern scientists. Can anybody name any one of those 7? One at a time, please. Yes.
Kepler, Newton.
Well, one at a time, and please identify where it is on the screen.
Kepler is the first.
The first one in the first row. All right. We'll take somebody else for the second, for another one. Who else would like to say yes?
Isaac Newton, the second one.
The second one on the left in the first row. Anybody else?
So,
Okay, go ahead.
the next one I think is Boyle.
No, the next one is not Boyle. There's no Boyle in the picture.
That one over there is Faraday. Faraday. Faraday.
Faraday is the one to the furthest right on the top row. That's correct. Michael Faraday. Any other attempts? You have anybody? But would you like to take a shot?
One is right, Linnaeus.
He always gets Linnaeus. Linnaeus is the one, the third one, and it was said some time ago that maybe Linnaeus had more influence than Jesus. I don't know if I would go with that. In fact, Linnaeus would probably be turning over in his grave to hear such a statement like that. Yes.
The middle one in the bottom row is Louis Pasteur.
Yes, he is correct. Louis Pasteur is the middle one in the bottom row. Yes. Any others? We stumped on the other two?
Copernicus.
No Copernicus.
Oh, bacon.
No bacon tonight.
Dana-Bashian.
No. All right. The one on the left on the bottom row is James Clerk Maxwell. Died tragically at 48. And the one on this side, think of your thermometer. Kelvin. Lord Kelvin is correct. What else did these men, as well as those others in this list, that includes the 7 you saw, have in common?
We're Catholics.
They were not evolutionists. There were some people in those days who were, but not too many. Now, let me step outside the empirical frame for just a few quotes, which you can see on the screen, because that book that we hold to has some interesting quotes that have a great deal of bearing on the sciences. Take, for example, the one in Job. Where were you when everything was formed? I like the next one below it because I'm a mathematician by trade. Adding one thing to another to find the sum. Also, come now, let us reason together, says the Lord. And that one at the bottom has to do with the indivisibility of matter. Half of it he constructs an idol, and the other half he warms himself by the fire. Does he not have any wisdom, in other words? Also, I'd like to mention for those in the viewing audience who think that I'm just putting together things, this is a copy of the Phi Lambda Upsilon Register, the official publication of the Chemistry Honorary Fraternity. I'm a member of this organization, despite being mostly a mathematician. I wear that badge proudly. Just one moment, please. These are a list of references that I used. The ones that are in green are favorable to creationists. The others are secular, which may be neutral or otherwise. I want to also give some credit for the slides. Joe Emilio, who is, I believe, now gone from this area, was responsible for a lot of those picture slides. And also, Tom Canfield had the touch-up slides, and also number 12. And Chad Williams also gave us one slide. The end. There's a list of the 16. Now, do we have some questions?
Go back to the picture of the people. The one in the red suit, you didn't tell us who he was.
Yes, we did. It was Linnaeus.
Oh, Linnaeus.
Yes. Bazille came up with the name.
All right.
Carl Linnaeus. Yes.
One of the first things you mentioned is that the universe couldn't have been always existing because it would have dissipated already. Can you elaborate?
Okay, the question is regarding issue number 2. I'm sorry, is it 2 or 3 you're referring to? Right, I've got them up on the board there, you can see. Did the universe always exist? As I said, the answer is no, because if it did, we wouldn't be here. Everything would have already dissipated. This is the second law of thermodynamics. If it had always existed, not merely existed for a long period of time, but always, then would have already reached that equilibrium state where nothing could occur. That's the meaning behind that statement. Do you have any other thoughts about that? Okay. Are there any other questions or concerns? Any others? Yes.
Shouldn't the Hubble telescope be able to see the Oort cloud?
Should the
I know they invented the Oort cloud.
Hubble telescope be able to see the Oort cloud? Well, the trouble is the Oort cloud is dissipated apparently in all different directions. It's not just in one little spot. However, if somebody comes along and says, okay, there's the Oort cloud and it's the one responsible for the comets that we can otherwise account for, fine, I'll just take it off the list and maybe displace it by another item instead. But nobody has, the problem is we don't have anything that's finally, refined enough to observe small comets, but if we did, well, fine, we could go after it. The point, however, is that people are making the claim, and those that are responsible for making the claim are the ones responsible for producing the evidence for the claim. Otherwise, it's an unsubstantiated claim, just like anything else would be. Now, if somebody could say, well, it's going to take us a while. Fine. Then I'll just wait. And wait. And wait. Till you come up with something. All right? Anything else? Yes?
I just want to clarify, number 7, how do any stars exist?
How do any stars exist? Number 7, yes?
Yeah, so the way it was explained was that it can't form because the gases heat up, and as they heat up, they'll end up cooling off. Did I understand that correctly?
Well, the problem, first of all, is from the standpoint of the Big Bang, as I explained earlier, the particles are going to go in all directions anyway, and at nearly the speed of light, too. And the farther they get from each other, the less chance they ever have of coming together. That's problem number 1.
So it's mainly in regards to the Big Bang. Because, I mean, there's like nebula, right?
Yeah. Of course, you'd have to explain how they got there. And not only that, but haven't you noticed that nobody ever tries to also frame the question of whether we get stars, whether or not we're just seeing stars that those dust clouds are now finally revealing instead of that they're actually forming? This is the problem I have. Nobody even brings that up. Instead, you have people on the air like Scott Pelley a few months ago said, there is a new star being formed. And, yeah, great. Well, let's see whether or not we can examine that some further. Yes?
Well, with respect to number 7, the unstated presumption of most of the people who talk about it is that gravity is the major force that will be doing things.
Yeah.
You were explaining that doesn't overcome Boyle's law and so forth.
Among other things. See, the question had to do with gravity and why gravity wouldn't be the explanation. Well, we have two major wands going around, actually about three, come to think of it. We have gravity, we have supernovas, and we have time, right? And if nothing else will suffice, we can wave the magic wand of one of those three, or in combination with the others, and maybe some more. Gravity is the weakest of the four fundamental forces. The only reason that we know anything about it is because we have a massive enough platform to experiment on to find it. That would be the Earth. If you want to do finer gravity experiments, you can with smaller objects, but you'll have only a tiny force. But per unit mass, gravity is the weakest of the four. And gravity will not pull together things that are already flying apart. And even if you did, as I mentioned earlier, even if you got, say, the hydrogen to come together, then the hydrogen will liberate whatever little heat it was, and it will actually get colder. This is a problem. But again, as you were explaining, now in the case of if it actually were to heat up, then the problem isn't gravity anymore, it's the thermal problem of gases flying apart from each other, which is what you'd have once you have it heated up to the point of being a gas. And you may consult either one of these two textbooks if you like. This was my undergraduate, Gordon Barrow physical chemistry textbook, or my graduate Moore physical chemistry textbook. Or you can even find some of this stuff in this book on physics, which many of us know as Halliday and Resnick. This is, of course, a standard text. It's probably still used to some extent. Do we have any other questions, concerns, comments? Any at all? Well, fine. You can see me afterwards then.